Hey guys, Chris the Lazy Geek here and welcome back to the channel. Today we're going to be talking about this set of two filters, the Askar Color Magic D1 and D2 filters. And this is actually by popular demand because previously on the channel I reviewed the ultra budget Askar Color Magic C1 and C2 filters, which allow you to do on the cheap a Hubble palette with one-shot color astrophotography cameras. Or DSLRs for that matter. And the D1 and D2 basically does the same, but much better and more expensive as well. And a lot of people on that previous video about the C1 and C2 asked me to test the D1 and D2, and that's where I am. And also, where did I get those filters from? I got them from one of my subscribers and Patreon supporters, Dave, and they are on loan, so I will be sending them back to Dave afterwards. And also, because they don't come from the manufacturer, we know it's a random sample, and so it should be fairly representative of the actual filters that normal users get. And this is important because if you've watched my channel before, there is a lot of filter lottery going on with specifically narrowband filters, which those two filters are, in that you have some filters that perform better than others even though they're the same brand, same model, etc. And a lot of filters actually don't perform up to specs, so it's always very interesting. Anyway, what are those two D1 and D2 filters? Well, the D1 is a filter that blocks everything except H-alpha, hydrogen alpha, and oxygen 3. And the D2, it blocks everything except the sulfur 2 and oxygen 3 band passes. So what this means is using the D1 and D2, if you use them like 2 nights in a row, one full night with the D1 on a nebula target, and one full night with the D2 on also the same nebula target, an emission nebula, you will be getting 1 night's worth of hydrogen alpha, 1 night's worth of sulfur 2, and combining the two, 2 nights worth, of oxygen 3, which has typically the lowest signal to noise ratio and the most affected by light pollution. So it's a great compromise to have. And I've shown in a previous video how to process the data from such filters, where I used the C1 and C2 filters as an example. I'll put the link down below up above. I'll also have the links to all of those filters down in the description if you're interested. Okay, so why are those two filters different than the C1 and C2 filters? The difference is the band pass, the width of the band pass, as well as the blocking characteristics of the filters off band. The C1 and C2 filters, they're cheap, but they have wider band passes, meaning that when they pass like H-alpha, sulfur 2, oxygen 3, they also pass a lot of color around those target wavelengths, and therefore a lot of light pollution in there as well. And also off-band, in the areas where they're supposed to block all light, the rating for the C1 and C2 is, I think, OD4 or even OD3. Lower number is worse. And so even off-band, the C1 and C2 do let in a little tiny bit of light pollution. Now the D1 and D2, they have much tighter band passes, so they let in much less light pollution. Specifically, both of them on oxygen 3, they have 6 to 7 nanometers of full width half max band pass. And on H-alpha and sulfur 2 respectively, they have between 8 and 9 nanometers of full width half max band pass. And so these are proper narrowband filters that you can use with color cameras. At the same time, off-band, so outside of the areas that they're not supposed to pass, they are certified in specifications to OD5 or better, which is basically the gold standard. We're really rejecting most of the like 99.99999% of the light off-band, at least. And so that's where we see that the price for the C1 and C2 was $190 roughly. And now the price for the set of the D1 and D2 is, I think, $549, so more than twice. Because yes, those filters, they're more difficult to manufacture and they also have much better results, especially in cities like Tokyo. Talking about results, in this review I will not be showing like a nice fully processed final image, because final images, I can get great final images even with potato filters and potato equipment, and it doesn't really tell you that much about the filters themselves. Also, the weather has been really bad and I've been having those filters with me for a long time and I need to return them to their rightful owner. But I will be showing you samples of 1 hour of exposure time on the Horsehead Nebula with the super bright Alnitak star in the picture, so we can see whether those filters cause any halos. Because I know a lot of you guys hate halos from your filters. And I might have some good news on that front, but to see the good news, you'll have to stay tuned and watch the video till the end. And while you're staying tuned, by the way, you could scroll down, like that video, subscribe to the channel if you're new, in which case, welcome to the channel. Leave a comment, tell us what you think about this. And if you want to support the channel, you can also use my links in the description to buy stuff. Anything really, or join my Patreon as a member, or my channel as a member. Every little bit helps, and it's thanks to you guys that this channel is possible. Anyway, when I am testing filters, the most important thing to me is whether they perform to specification from the manufacturer. And so for that, I use a spectrophotometer, the Goyalab Indigo, that's from a French startup company. I use it with a light from the same company, and it's precise to roughly 0.5 nanometers. So it really gives a good idea of how well the filters are performing. And of course, I did the test with those two filters. Let's have a look at the results. Okay, now we're looking at the spectrum of the D1 filters, the one with oxygen 3 and H-alpha. So to tell you what we're looking at, on the x-axis, we have the wavelength, so the color of lights that it gets through, and on the y-axis we have the transmittance in percent. And due to the characteristics of my spectrometer, they're usually underestimated. So the actual transmittance is higher than what you see, and it is more underestimated the tighter the bandpass is. Okay, so now we can see we have two bandpasses as expected. The one on the left is for H-alpha, the one on the right is for oxygen 3. And you can see I have a cursor there, that red cross, and you can see the numbers here changes with the number for the x-axis, which is the wavelength, and then the number for the y-axis, which is the transmittance in percent. So let's first look at oxygen 3. So oxygen 3, if I look at the top peak really of the bandpass, it's actually 499 rather than the 500.8 nanometers that we want. So it's not quite centered. If we go towards 500.5, here we are, and 501. So basically the actual oxygen 3 main bandpass will be around here. And there's actually also a secondary wavelength for oxygen 3 that is 496 nanometers that is passed here. It's roughly like 1/3 of the strength of the main one. So by default, this filter passes both. The main is passed at around like, with my spectrometer, 78, between let's say 75 and 78% transmittance. Because of the tight bandpass, it's likely more than that, probably above 80%, which is very good. And the secondary bandpass, which is typically not really targeted by those filters, is still passed at around 35, 36%. So maybe 37, 38% in reality. So this is actually pretty good to see. Slightly off center, but still pretty good. Now looking at the H-alpha, we're looking at 656.3 if I remember correctly. So it's basically perfectly centered. So H-alpha is perfectly centered. So that's great. You can see that. And also you can see it has like a transmittance of around 88%, which again is probably around 90% in reality. So again, really good. And let's look at the actual full width half max, which is basically like the width of the bandpass at half of its intensity. And so if we take roughly this point here, 496 to roughly that point there, 503, we can see we have 7 nanometers full width half max. And the specs say that it should be between 6 and 7 nanometers. So it is as per spec. Let's look at the H-alpha. So we're doing the same thing. You can see we're at 652. Let's go to the other side. It's a bit more difficult, but roughly 660. So we have 8 nanometers to 8.5 nanometers of bandpass, and that's exactly in the middle of the specs, which is 8 to 9 nanometers. So on the D1 filter, we are very much respecting the specs. We have a slight off-center in oxygen 3, but that's really not a big deal at all. Okay, let's have a look at the D2 filter. Okay, and now we're looking at the spectrum of the D2 filter. By the way, feel free to completely ignore this part to the left. My source of light for the spectrometry is not reliable from around 420, 430 nanometers, so we can completely ignore that. But let's have a look at the D2, and we can see we have 2 nice band passes again, and we have oxygen 3 on the left, and we have sulfur 2 on the right. We can immediately see the shape of sulfur 2 is a bit weird, but I'm sure it's gonna do well. So let's look at oxygen 3. The peak is around 500.5 nanometers, which is exactly what we want. So if for this particular filter, this is better centered than the D1 filter that we looked at. And we can see the transmittance is more than 81%, because again, I'm underestimated the transmittance. So this is very good to see, very well centered. And we still get probably 496, right, yeah, roughly here. So the secondary oxygen 3 wavelength is still captured at roughly 21%. Okay, what about sulfur 2? So sulfur 2, we're looking at 672 nanometers. Where is that? It is here. So it is, again, pretty much bang center in the bandpass. This is actually really impressive for randomly selected filters. And we can see the transmittance is around 80%, actually more than that, because again, we are underestimated the transmittance with my filter. So this is also very respectable. Let's look at the full width half max. So on the left-hand side, we're going to measure from here 497 to roughly here 504. So again, 7 nanometers bandpass within spec. And let's look at the one on the right. So for here, yeah, from here, so 667.5 to 676.5 roughly. So this is 9 nanometers of bandpass. So it's also exactly as per spec, although on the higher, meaning worse end of the specs, but still within specs. And so we can see that these filters, they perform basically up to specs. And that is, I mean, it should be normal and nothing impressive at all. But I have tested so many filters that do not perform to specs at all. Now, one limitation, of course, of my spectrophotometer is that I cannot tell you what the off-band blocking actually is. I'm not able to measure that. So for that off-band blocking, we have to trust the manufacturer with their OD5 or better rating. Specifically, I know that these filters will provide a good result in light polluted areas, like here in Tokyo, thanks to their narrow band passes, relatively speaking. And at the same time, because their band passes are not too narrow and they're fairly well centered, I know that they are both going to be very resistant to something that is called bandpass shift, which happens when you use very fast optics like RASA or Hyperstar optics at f2, or maybe camera lenses at f2.8, f2, sometimes even f1.8. Basically, when light reaches those filters at an angle, the bandpass that those filters pass is actually shifted. And it's shifted towards the blue, so it's called the blue shift. And it shifts much more for H-alpha and sulfur 2 than it does for oxygen 3. So oxygen 3 is almost never a big concern. But on those filters, because the bandpass in H-alpha and S2 is fairly wide, 8 to 9 nanometers, and at the same time, at least on my sample of those two filters, it's well centered, it will work very well with fast optics. I probably would even be using those filters without really issue with my old Hyperstar at f2 telescope. So now that we know like how well those filters are going to perform, I need to show you how well they performed on Alnitak around the Horsehead Nebula. And for that, I used 2 nights. The Horsehead Nebula is getting low in the sky even from the early evening these days. But I used 2 nights. One was with the D1 filter, the other was the D2 filter. And this was using my fairly fast Newtonian telescope at f3.5. That's a great use case. because we do have quite a bit of bandpass shift happening there. So for both the D1 and D2, I took 1 hour of data each. And it is to note that on the first night it was very hazy. Okay, and here we have it. On the top is the image of the D1 filter, so H alpha and oxygen 3. And on the bottom, we have the image of the D2 filter, which is sulfur 2 and oxygen 3. I didn't take any calibration frames or anything with those two filters, and there's not even background extraction done. This is just like the raw image with an unlinked stretch with the screen transfer function. And we can see we have our old friend Alnitak here. And what do you notice on both images? So first we can see that on the first image, Alnitak is definitely much less bright, and this is because of the haze that we had. But it's still plenty bright. And on the second image as well, it is very bright. And what do we see? We don't see, I can tell you what we don't see. We don't see a halo. There's no halo. I mean, there's a bit of like fuzziness around the core of the star, but that could be the camera as much as it could be the filter. So that's actually really, really good. And I'm surprised because I always see halos on Alnitak to some extent, but not here. So there you have it. It looks pretty neat in terms of 1 hour of data when the nebula is like low in the sky from Tokyo and there's no halo. Okay, so now we've seen how well those filters perform, and I think they perform up to spec and no halos. That's like what most people want. But are they worth the price? In particular, you can get the Optolong L Extreme, which has narrower bandpasses, which is better, for around $300. And you have also something like the SVBONY SV220 filter, which I've never tested. That's like ridiculously cheap, something like $150, and it's also tighter bandpasses than the D1. But both of those filters would be a replacement only for the D1. And it is to be noted that I have tested quite a few Optolong L Extremes, and their specs are not very consistent. When I looked at the bandpasses, often they were really not up to spec. Whereas I look at the D1 and D2 here and they're perfectly up to spec. Maybe it's just luck, absolutely possible, but it's something to keep in mind. But that means that if you want to save money, you could, for instance, not buy the D1, buy like the SVBONY instead, the SVBONY SV220. I'll put links down in the description, of course, and then buy the D2, and you can still do the Hubble palette as long as you have like one filter that passes oxygen 3 and H alpha and the other that passes sulfur 2 and oxygen 3, you're good. So you can mix and match the D2 with something else. Heck, you could even like take the C1 and the D2 and make a Hubble palette. So we have a lot of options here. And so I think it's definitely something to keep in mind if you're looking for filters. And of course, as usual, do your homework, look at other potential filters that you could be using. With that, thank you so much for watching. As always, leave a like, subscribe, leave a comment, etc. Every bit helps out. But more important than all of that, don't forget whenever you can to look up at the stars, and I'll see you next time.